Hi everyone, I'm Devika Tharakkal and I'm a PhD student at Newcastle University working with Anwar Shukrov and Graham Sarson. And today I'll be talking about nonlinear magnetic buoyancy instability in galaxies. This is a work I've been doing with Fred Gent, Anwar Shukrov, Graham Sarson, Andrew Snowden, and Luis Felipe. So to begin, I'll give a brief introduction and theory behind magnetic buoyancy instability. We know that when we model the dynamics of interstellar medium, it is driven by the main energy components, which are plasma, cosmic rays, magnetic field, and gravitational forces. So the idea is that when a dense fluid like plasma is present along with a lighter fluid like magnetic field or cosmic ray, which is energetic but weightless, it can cause a buoyant forces in the system. And this buoyant force, along with vertical stratification, can result in instability under the right conditions. So here we have a cartoon which shows a disk galaxy with a gravitational force acting towards the center of the galaxy and a magnetic field in the horizontal y direction. So the vertical direction is Z and the horizontal direction is Y. And this system is assumed to be vertically stratified. That means that the magnetic field and the density, plasma density, they are functions of Z. So if we have these profiles and if at time t equal to 0, that's at the initial times, if we consider all these profiles to be in a magnetohydrostatic equilibrium with the gravitational force, then a slight perturbation in the system can cause the plasma or like the gas to rise through Z from a denser to rarer region, pulling the magnetic field lines along with it. And due to the buoyant force, they'll keep rising. And under the right instability criterion, this can result in the whole system to be unstable. So this is basically magnetic buoyancy instability. And if we include cosmic rays to the system, this instability is more generally known as Parker instability because it was first studied by Parker in the regime of galaxies. So Parker assumed isothermal gas disk with a uniform gravity present throughout the system. And what he saw in the system was that initially horizontally aligned field lines, due to the rise of the instability, they become bent and looped due to the undular modes of the instability. So the bending and the twisting of this, bending and looping of these field lines can render it less efficient in holding or containing this gas, which was initially held up because of the buoyant forces. And this will result in the gas to fall down to the lower regions where the field lines are more concentrated. So we see valleys where the gas gets more accumulated. So this is the final effect of the instability. And this is what we are trying to study and how this instability would rise and saturate in a system. So initially, we tried to understand the system with just magnetic field and slowly move on from this case to the case with cosmic rays. So in order to do that, first we look at the equations of motion that's necessary in the system. So we have three equations of motion. First is the equation of continuity, the induction equation, and the momentum equation. So first, we initialize a background state ρ0 and b0 for magnetic field and density. And these are assumed to be constant in time. So they're functions of Z and they're assumed to be constant in time. And what we are evolving is the deviations from this background state at each time. So when we initialize ρ0 and b0, we force it to be in a state of magnetohydrostatic equilibrium with the chosen gravitational profile by choosing the correct parameters and correct temperature. And this is an isothermal system. And we also force the background state. I mean, we're not forcing. So we're imposing the background states to be constant in time. So they do not change throughout the simulation. We only evolve the deviations to these background states. So in order to solve this, we use pencil code, which is a higher order differential equation solver. So we put all these equations through pencil code and evolve them in time. to see how the instability grow and saturate. So the box that we choose here is a cuboid, which is horizontally slightly longer than the vertical directions. So vertically, we have around 3.5 kiloparsec, and horizontally, it's around 4 times 4 kiloparsec square. And the boundary conditions are such that in X and Y, we have periodic boundary condition, and in Z, at the vertical boundaries, we choose the boundary condition such that it allows for some outflows in the system. I'm sorry. So now we have the equations of motion and the initial setup. So now I'll show the evolution of the instability for one of the simulation that I ran choosing this gravitational profile. And this is from the work by Quick and Gilmore in 1989. So what I've shown here is the evolution of the instability from 10 megayears to 800 megayears. And what I've plotted here is the density profile, which is shown in the brown and purple color, superimposed with magnetic field lines for a Z-Y slice at a fixed X value. So what we see is that initially the field lines are in the Y direction. And as we move in time, we see that the field lines bend and loop, and we see them being rarer and denser at certain regions. And as we move further into the nonlinear stage, we see accumulation of density near the equator with peaks forming around there. To understand this a bit further, we look at the horizontally averaged profiles that is shown on the left-hand side here. So we have 3 figures, which is the first one is the density, second one is the magnetic field, last one is the velocity. So the profiles are at 2 different times. So the solid line corresponds to the linear time, that is 300 megayear, and the dashed dot line corresponds to non-linear time, that is 800 megayear. So we see that the density at Z equal to 0 increases as we move from linear to non-linear. The magnetic field becomes weaker as we move from linear to non-linear. And the flow velocity increases as we move from linear to non-linear, and also as we move away from Z. So we'll talk a little bit more about the evolution of this profile later because it has some interesting parameters. But before we do that, I also would like to show you the nature of the solution by looking at some spatial cross-sections in the system. So here what I've taken is XY cross-section at Z equal to 500 parsec for both magnetic pressure and density at 2 different times, that is linear and in the non-linear phases. So in the linear stage, we see the density being like the perturbations, they are well ordered, and like we see the linear nature of the solution by seeing well-formed peaks and valleys. And as we move from the linear to non-linear stage, we see that the system gets much more disordered and inhomogeneous. So the system gets more complicated as we move from linear to non-linear stage. To understand the nature of the solution a bit further, we also look at the Fourier spectra. So what I've given here is the 2-dimensional Fourier spectra for fixed Z and Y values, and also the 1-dimensional Fourier spectra for these slices, which is corresponding to the power spectra with respect to KY and KX. So from all these plots, what we try to do is to isolate the most unstable mode for each Z, which drives the instability at that particular set. And what our final goal is to isolate these K unstable modes, the wavelengths corresponding to these unstable modes, and to compare it with some known dispersion relations and to see how well our model works. So from these plots for this particular gravitational profile, we see that the most unstable mode corresponds to KY at around 5 inverse kiloparsec with the KX at around 0. This is at Z equal to 500 parsec. So before we plug this into the any dispersion relation, we also need to study the evolution, or like to understand the distribution of growth rates in the system. So to do that, we look at the URMS squared value at different sets. So the evolution of this value at different sets. So that is given in the left-hand side panel. So here the solid line corresponds to near equator, and the dashed dot line corresponds to at around 300 or 400 parsec, and the dotted line corresponds to near boundary value. So we see that as we move away from 0, the growth rate increases, and we have a faster evolution of UZ at higher altitudes. So this is shown in also shown in the middle figure, which is the distribution of growth rate omega with respect to Z. So we see that as we move away from 0, we see a higher growth rate. We also try to isolate the wavelength corresponding to the most unstable mode. And we see that even though it varies slightly with Y for this gravitational profile, it has almost remained near the value of 0.8. So these both are dimensionless values. So now we have the growth rate and the wavelength of the most unstable mode. So now we can compare our runs with known dispersion relation to see how well our system works. So we take a simple dispersion relation model. So the one that I've chosen here is from this book by Shukrov and K. Subramanian. So here, the main assumption is that the kx tends to 0 and we have kz is equal to 0. So the whole dispersion relation is only dependent on the magnetic pressure ratios and ky value and growth rates. So from this plot, we can see that the curves correspond to the theoretical value and the dots corresponds to the numerical values from for different parameters in our simulations. And we see that they're in good agreement, showing that our simulations are in fact a good model to study and understand the nature of this instability. So that's the linear phase. And as we move further into the nonlinear phase, I want to talk a bit more about the evolution of the profiles. So what I've plotted here is the horizontally averaged profiles for the perturbation and the total values of density and magnetic field at different times. So this is no longer in the linear phase. So here I've plotted it from 400 to 700 megayears, that is early nonlinear to late nonlinear stages. So we see that the perturbation becomes more and more stronger as we move further into the nonlinear phase. And especially for magnetic field, this perturbation becomes almost comparable to the initial values of the magnetic field we had in the system. I'm sorry. The value of density. So if you look at the horizontally average density profiles, we see that there is a increase in the peak value at Z equal to 0. But we also see that the nature of the profile, that is the distribution, changes significantly as we move from linear to nonlinear phases. So we try to fit these curves at later stages, and we see that there is a decrease in scale height. So we try to fit the values from between -1 and 1 kiloparsec, and we see that the scale height varies from around 500 to 300 parsec. So the entire nature of the density distribution changes at the late nonlinear stages. This case is similar in the case of magnetic field distribution. So we see that the whole distribution flattens significantly. And so this is probably because we have a very strong Vz component forming in the system, which becomes almost comparable to the Vy value. So the entire nature of the initial profiles, the total profiles that we had in the system changes as we move further into the nonlinear stages. So to understand it a bit more, so we look at the different force components in the momentum equation. So given the time evolution of the magnetic pressure, density, thermal pressure, magnetic tension, and gravitational pressure forces. So the gradient of these forces, the gradient of these pressures. So basically the force components at different times, that is 200 megayears, 300 megayears, 500 megayears, and 850 megayears. So that is linear to late nonlinear. So in the first two columns, that is the linear stages. So we see that the ratio of magnetic pressure to thermal pressure, they are unity, because that's how we had initialized the system. We don't see much difference, and the magnetic tension was almost non-existent here. But as we move to the late nonlinear stage, where we see the explicit formation of these magnetic loops, field line loops, so we see that the pressure drops down significantly and the tension force increases, but they are in the opposite sign. So we see a significant, so we see that the magnetic pressure force becomes very much less than the initial value. So they become almost half the value. And the thermal pressure force here, it has increased significantly. And if you move one more column to the right, we see that the pressure forces, the magnetic forces have fallen down even further. And what we have here is a very dominating thermal pressure force, which is entirely dominant all over the box. It is also interesting to look at the evolution of velocity and momentum flux throughout the system. So what I've plotted here, the two columns, is that on the left column, I have the vertical velocity component, which is divided into three parts. So the one green dashed line is basically the positive component of the vertical velocity. The orange dashed line is the negative component of the vertical velocity. And the purple line is the total vertical velocity component, and at different times. And on the right hand side, we have the momentum flux corresponding to the vertical velocity component. So as we move down in time, we see that as we move away from equator, the momentum flux becomes stronger, either in the negative or positive direction, or the velocity too. But for a while, that is from 200 to 500 mega years, we see that the nature of this flow near the boundary is positive, and it suggests an outflow. So I think I forgot to mention this. So what I've plotted here is only for half of the simulation box. So this is the positive half of the box, that is from 0 to 1.75 kiloparsecs. So we see that at the first three columns near the boundary, we see a positive velocity. And if I zoom in here, we see a positive momentum flux. So this nature of the flow for a transient period of time was consistent in every single simulation that we ran, and this needs to be understood a bit further. But after some point, when the magnetic field components get comparable, there is some dissipation effects happening in the system, and we see a strong outflow generating in the later stages. The next step is to add cosmic rays to the system. And as I said before, cosmic rays are highly energetic, massless fluids, which can enhance the instability and can have significant effects on the saturation of this. So in order to do this, we model cosmic rays as a fluid. And so we have to add another equation to the whole system, which is given here. Here, epsilon CR is the energy density of the cosmic rays, PCR is the pressure of associated with cosmic rays, and F is the cosmic ray flux. And here we assume a non-Fichtean model for the diffusion of cosmic rays. So this is a work that is still going on, and I'm still analyzing the results. But from the preliminary analysis, what we see is that while the presence of cosmic ray enhances the instability, and like it results in the instability kicking in and saturating faster, the final stage of the simulation is comparable to the runs with no cosmic rays. We see the cosmic ray pressure and the magnetic field redistributing similarly, and we see the thermal pressure dominating at the final stages. But we still need to isolate and iron out the details of like the transient stages, if there is a stronger outflows, if the saturated final stage is slightly different from the state that we have in the case with no cosmic rays. But as I said, this is works that's still going on. So to conclude, the main points that I want to lay out here is that in our simulation, we see that the local growth rate of the instability is dependent on Z, and as we move away from the equator, we saw that the growth rate increases. We also saw a transient period of time where there is an outflow being generated in the system, and it was consistent every single run that we had, and this needs to be isolated and studied a little bit further. We also see that the density profile, nature of the density profile changes significantly, and the scale height of the distribution also changes. And this is the same case for the magnetic pressure, the magnetic field distribution. So we see a broadening or like flattening of the distribution that we had for the initial background state. And we see that the magnetic pressure force drops down significantly. So the next immediate future plan would be to add rotation, which will have like obviously dynamo effects in it, and to see how this would affect the nature of the instability growth and the saturation. I expect there'll be some impact on the instability growth rate and the linear phases. It'll be very interesting to see what will happen to the final saturation of the magnetic field lines and the magnetic pressure forces there, when we have an additional field generation of additional mechanism which will affect the magnetic field lines. Another thing to immediately do is to improve the cosmic ray models, to add more physics like streaming and other effects, to see how that would affect the entire system, like the growth and saturation. So that's what I wanted to say for today. Thank you for listening, and I'm more than happy to discuss and answer any questions that you have on this talk. Please contact me on this at this email address that's given below. Thank you for listening once again.